Thank you very much for inviting me to speak here. So I would like to answer this question for a certain tower of number fields. So for this talk, we will fix an elliptic curve over the rational numbers. And well, we know that if you're given a number field, then the f rational solutions of the elliptic curve with the point at infinity, they form a finitely generated group. So this was proved by Model 97 years ago in this thesis, and then later generalized by Weil to arbitrary number fields. Model had already proved this for f equal to q. So determining R is hard, but one might hope to say something about R as one varies f. So the question is, I fix E. I vary f. How does R vary? And since we're fixing E and varying f, let's record the dependence of this rank R, which depends on both E and f, just by R of f. Great. So you would like to look at a certain tower of number fields, the cyclotomic ZP extension of Q. So you start with Q, and I'll join a pth power root of unity, a pth root of unity. Then this field is different from Q as long as the prime P is not equal to 2. We can keep playing this game. We just keep adjoining higher P power roots of unity. So this means primitive mth root of 1. It's a notation used by the Russians in the old papers. Right, so we play this game. We'll notice that the Galois group of Q adjoint zeta P over Q is isomorphic to Z mod P Z cross. If you think about the Galois group of Q adjoint zeta P to the n plus 1 over Q adjoint zeta P, it's Z mod P to the nz. So the Galois group of the top guy over the bottom guy is just the product of these two groups. It's an abelian group, and we have all the power of Galois theory at our hands, so we can reverse the function of this guy and this guy. So instead of having this being the subgroup and this being the quotient, we can invert their roles, and from this we know that there's a field Qn, which is the fixed field of the top guy by a group that's isomorphic to Z mod PZ cross. We can play this game at any level in this tower. It's called the fixed field of Q adjoint zeta P squared by Z mod PZ cross. It's called as Q1. at the end, what we have is a tower of number fields where the nth guy has Galois group Z mod P to the NZ over Q. So all day, let P be an odd pram of good reduction. So over the finite field Fp, E is still an elliptic curve. So here's a miracle. If you look at the rank of the elliptic curve as it varies in this tower of number fields, then as a function of n, this is bounded. So at some point, it stops growing. So although you have more and more numbers available, the number of solutions inside your elliptic curve essentially does not grow. I was very shocked to learn this when I was a grad student. Another way to phrase this is to say that the Mordell-Weil rank at Q infinity is finite. So Q infinity here is the direct limit of these Qn's. So in other words, the union.
What about pole with unity?
Say again?
What about the right-hand side? It's bigger field.
It's still bounded. It's not hard to show because this is just a finite extension of Q. So you play the same game.
The top will be different.
It will be slightly different. So the top will still be an extension of Q infinity whose Galois group is isomorphic to Z mod P Z cross. So not very different.
How about the finite part?
Say again?
How about the finite part? The finite part.
Oh, hi, sorry. The finite part?
Yeah. So
The torsion part, you mean?
Yeah.
It also stays bounded.
Oh, great.
Yeah. So if you think about this, the Galois group of Q infinity over Q is the inverse limit of these guys. So it becomes isomorphic to the ring of p-adic integers. And this guy is called the cyclotomic ZP extension of Q. So here's an exercise in class field theory.
So this follows from similar calculation and then using open image theorem. How to prove this thing?
Can't roll it? Yeah, I'll prove it. Patience. As an exercise, Q infinity is the unique extension of Q whose Galois group is ZP. Nice exercise in class field theory. Great. Let's see. I think that's all I wanted to say about this. Now you can ask yourself what happens in the next simplest case. Instead of starting with Q, what if you look at ZP extensions of K, imaginary quadratic field? The analog of this exercise becomes that there exists a unique ZP squared extension. So let me draw the tower of number fields where I have space. So here. So you have K infinity at the top, K more or less at the bottom. At the very bottom you have Q. And this extension has a Galois group isomorphic to ZP squared. You can also look at ZP extensions. And the first example would be to play the same game that we played here. So you adjoin p-power roots of unity and construct the analog of the cyclotomic ZP extension, which is also called the cyclotomic ZP extension of K. I denoted this Q infinity because Q infinity is the analog of K infinity. But I could have also called this Q sig, the cyclotomic ZP extension of Q. And the theorem of Kato and Rohlich it carries over. So inside the nth layer of the cyclotomic ZP extension of K, the rank stops growing even when n grows. Right. So the Galois group of K infinity over K sig is ZP, right? The cyclotomic ZP extension has an evil twin called the anti-cyclotomic ZP extension. So this is another ZP extension. It's characterized by the fact that the Galois group of the nth layer of the anti-cyclotomic ZP extension over Q is isomorphic to Z mod 2Z, semi-direct product Z mod P to the NZ. It's a dihedral group of order 2 times P to the N. So I cannot draw all the ZP extensions because there's infinitely many. So infinitely many quotients of ZP squared. They all sit inside here. So what have we learned so far? We've learned that even though you have more and more points, it doesn't mean that the rank of an elliptic curve must grow. So applying this intuition to the towers of number fields starting with K, one might guess that the rank of an elliptic curve stops growing in any of them, but that is again false. So here's a theorem by Bertolini. And others. So Greenberg, Kony-Watzal, Longo, and Vigny. It says that, let me be a little bit vague about this, because the precise statement is not needed for this talk. So there are scenarios where the rank along the anticyclotomic ZP extension keeps growing. So this happens when the root number is equal to -1. For the opposite sign, this p to the n becomes a 0, and it's still bounded. So that's a surprise within a surprise. However, there's this conjecture by Maser which states that any other ZP extension of K, so any ZP extension other than the anticyclotomic one, then the rank should stay bounded. So this is some sporadic case. So if you have any ZP extension different from the anticyclotomic one, then the rank of this is bounded. So then we went ahead and asked ourselves the question, well, what can you say about this conjecture? What's the best statement you can make? So it's not hard to prove that all but finitely many ZP extensions satisfy this property. So for all but finitely many ZP extensions, the rank stops growing. But then we asked ourselves, well, what's the best statement we can make, which does not involve the statement all but finitely many? What can you say when you start the sentence with let L infinity be any ZP extension of K? How does the rank grow? So here's the theorem. If P splits in K and the class number of K is coprime to P, then the rank at the nth layer of any ZP extension is big O of P to the n. Let me actually write a more general theorem from which this follows. Instead of ln, let's look at kn. Kn is the thing in the middle here. So it's the nth layer inside the ZP squared extension, which contains the nth layer of the cyclotomic ZP extension and the nth layer of the anticyclotomic ZP extension. In fact, the nth layer of any ZP extension. The Galois group of this guy over K is Z modulo P to the nz squared. So the theorem says that the rank goes as at most this badly. Great.
Does the conjecture say this big O means with the 1, right?
See, the conjecture says.
I mean, they compare with combine with Bartolini theorem.
Oh yeah, so.
Right.
So the conjecture says it's
Big O be 1.
it's 2 times P to the n or 1 times P to the n. So I swept some technicalities under the rug. So the growth conjecture of Maser is a little bit more involved. He gives more precise predictions when the rank in the anticyclotomic tower should grow either like this, or there could possibly be a 2 in front of this, or 0. So the number in front of it is either 0 or 1 or 2, and this number he calls the growth number.
They exist a scenario.
Yeah, they exist. I was vague on purpose because I didn't want to write down this precise statement. But please read the introduction to my paper. Everything is written down, not very nicely.
So that you get king and a point, so you check the sign function.
Yeah. All right. So the ideas of the proof. So there's two techniques. One is old and one is new. The old one is the idea of controlling. It goes back to Maser's Iwasawa theory for elliptic curves. In one word, it's to try to control the rank at finite level at Qn or Kn sick by analyzing an object that comes from Q infinity or from K infinity. Once you're up there, then you somehow are able to control what's going on below. I picture this always as somebody having a puppet and pulling some strings. So that's the old idea. The new idea that's new in this paper is, so we don't really have a good name for it yet, but it's something like we look at certain localization maps and use them in tandem together to wiggle out a good estimate how to stop the rank from growing. So let's go back to the basics. In the simplest case, you're only looking at the q rational points of the elliptic curve. So that's this guy, right? Well, if you tensor this with q mod z, you can embed this inside the Salma group. So a group coming from Galois cohomology, which is used to cheat a little bit, to fake construct rational points. And this process of cheating is conjectured to be not too bad, because the co-kernel of this appearing in this exact sequence is conjectured to be finite. Schaffer-Ridge-Tate group. So then in the 1970s, Maser had the idea to look at this short exact sequence, not only for Q, but for any of these number fields appearing in the cyclotomic ZP extension. So you can look at, oh wait. So if you tensor with q mod z, then what happens to this guy is z becomes q mod z, and the finite part gets tensored away, which is fine because we're only interested in the rank in this talk. So if you do this if you play this game for qn, you get an exact sequence like this. And you can simplify this even further by looking only at the p primary part of this. So if you look at the p primary part of these guys, then on this side, looking at the p primary part of q mod z is like saying, look at qp mod zp. So no information about the ranks has been lost. But the notation has become a little bit convoluted. So let me call this module simply mn. So now, Mn, well, it's a group. But it's not any group. It's a group with an action of the Galois group of Qn over Q. So it becomes a module over the group ring Z adjoined Galois group of Qn over Q. And you can play the same game when you replace Qn by Q infinity. So the primary part of the Salma group over Q infinity, let's call this M infinity, is a Z adjoined Gal Q infinity over Q module. We're only looking at P primary parts, so these modules are actually ZP modules. And M infinity is the inverse limit, the direct limit of these MNs. So you can consider this as a module over the completed group ring ZP double adjoint Gal Q infinity over Q. And the observation of Serre in the 1950s, 1960s was that when he studied the work of Iwasawa, discovered that this is isomorphic to ZP double adjoint X. So in the end, you're faced with the challenge of analyzing a ZPX module M infinity to say something about the ranks. The idea for the proof of Kato-Rowley. So now I'm answering your question, Shabu. The idea for Kato-Rowley. You remember? Okay. Let me remind everybody else. Is to say, well, this rank is, well, it's the number of times QP mod ZP appears in here. It should be the same as the number of times QP mod ZP occurs in Mn. But we don't know this because we don't know that SHA is finite. So we know this is less than or equal to the number of occurrences of QP mod ZP in Mn. And we want to say that this is less than or equal to something pertaining to the module at infinity. So this something is the ZP rank of the dual. The Pontryagin dual is used here because what it does is it converts every copy of QP mod ZP into a ZP. It's easier to handle. What I left out here, what's strictly not necessary at the moment, is that this is, of course, bounded by the ZP rank of the dual of the submodule, that is the invariance by the Galois group of Q infinity over Qn. I hope you can read it. It says Galois group Q infinity over Qn. So in order to make this work, one needs to know that this guy is finite. If you can show this, then we're done. So here's a theorem which works in one case. So in this paragraph, let's assume that P does not divide AP. AP is the difference of the number of FP rational points of the elliptic curve with the number of rational points you would expect on average. So P plus 1 minus the number of E, FP. So in this case, Kato proved that the dual of M infinity is a finitely generated torsion a ZPX module. Step back and pretend that I wrote Z module instead of ZPX module. This would be saying that M infinity dual is a finite abelian group. So it's the ZPX module theoretic analog of finite abelian group. The theorem of USR says that such a a module has finite dp rank. So if you combine these two theorems together, you get that this is finite. So then that's the idea behind Kato-Rohlik. Except I cheated. So I cheated here. So why is this inequality true? It is true because of Mazur's control theorem. So the part of the control theorem we need states that if you look at the natural map between Mn, so the Selma group at nth level, I2, well, the way to fake this Selma group at finite level using only the Selma group at infinity this guy has finite kernel. So those who have seen Mazur's control theorem before, I mean, of course, there's much more to this. The co-kernel is also finite, and one crucial benefit of this control theorem is that the size of the kernel, the co-kernel, is bounded as n varies. But all we need is that the kernel is finite for this talk. So once you know this, then you're done. You know that these dp ranks match up. The control theorem and Kato's finitely generated torsion theorem both need that P does not divide AP. But before we discuss the case where P does divide AP, let's generalize this all to K. So instead of looking at where are we? 3b at Q. Let's look at K. So everything I said, you can carry out for K instead of Q. Just formally replace all Q's with K.
What is K?
K is the quadratic imaginary field.
But you still take n level, right?
That's correct, yeah. So one difference is that the number of variables changes here. For this, you need that P splits. And then the theorems that I wrote down for Q are still true. This is a theorem by an order. This theorem is not true for K. Now the idea then is to try to carry out the same strategy as in the world. We started with Q. one difference that happens when you look at k instead of q is that this O1 becomes O p to the n. So to give you a feel for this, oh, sorry. That's correct. Thank you. That's why I said it's this. This inequality here is strictly not necessary for if you just look at Q, but for K it is. So a toy example is where the dual is, say, something like this. It's torsion over zpxy, but it's not quite ZP.
Cyclical, which direction?
Sorry? It doesn't matter which direction. I mean, you can also model by x. I mean. Oh, wait. That's what you I see. Sorry, made a mistake. Well, yeah. If you look at this, then the strictly speaking, this shouldn't be m infinity fixed by gal k infinity over k, but m infinity k fixed by gal k infinity over k dual. So the gal k infinity over kn dual part then is is isomorphic to something like this, which has ZP rank p to the n. Great. So this is the basic strategy in the case when p is ordinary, and this is the first theorem in our paper. But at this stage, we wouldn't have written the paper because these arguments are all very standard and well known to the experts. In fact, I think the theorem itself was just not written up. The point of this paper is to scrutinize the case where P divides AP. So in this case, there's a nice theory when AP is equal to 0. Youngdu Kim came up with the control theorem, building on earlier results of and ideas of Kobayashi and Pollack. So very briefly, the idea is the following. There's a somewhat canonical way to split up the kn rational points of the elliptic curve into two parts, a part that people call the plus part and a part that people call the minus part. And if you look at the plus parts and the minus parts separately, you can still construct analogs of these guys. So the Selma groups at level n. You can construct mnk plus, mnk minus. And if you play a similar game as we just played, at the end you get a module at infinite level. And if you look at the dual of that guy, then this dual satisfies the conclusion of the theorems of Kato and Van Order. At least it should. Not only do they satisfy the analog of Kato and Van Order's theorem, but also the analog of the control theorem. So then you can play the same game and bound the ranks. So at this part of the paper, I mean, the arguments were a little bit more involved, but it's still not that new. The only thing that was new, if you look at our papers, there's some somewhat ridiculous diagram that if you want to read it, you need a little bit of a sense of humor. A little bit afraid that the referee would say something, but they didn't.
What plus was minus something?
Second?
The plus minus was that?
Oh, I did not define this. I can maybe after the talk if you want.
So E is still defined over Q, not K.
That's correct, yeah. In this entire talk, in this paper, E is defined over Q.
And you use this to define plus and minus?
No. Yeah. So, there's a sequel in progress.
Now you have a P equal 2, A P equal 2 or 3.
Yes, when so P is bigger than 2 all day, right? So what happens at the most difficult prime, P equals to 3? So what happens if P divides AP, but it's not equal to 0? Maybe I should write out. That the normal control theorem, if you just look at the Selma groups, that is false, because what happens is that the Selma group turns out to be a rank 1 cotorsion ZPXY module. In this case, there's no control theorem. So neither a normal control theorem as above, nor a BD Kim style control theorem. So what do you do? Well, so our strategy is the following. The first part is to control whenever you can. Mn K, say, is I've been ditching the definition of the Selma group, but I think now I have to use it. So you look at the localization maps at each place, V of K, inside the H1 of the local version of K and EP infinity lie the local points.
Sorry, when you say there's no control theorem, you mean that such a theorem is false or not proved?
It's not stated.
Should it be true?
I mean, it's not clear what the statement is.
So for example, that statement there,
This one.
the direct analog of Mazur's statement.
Yes, yes. That is false.
That's false. And why is it false?
It's false because the definition of the plus and minus does not work when AP is not equal to 0. So there's a different definition. There's a generalization of this plus minus theory called the sharp flat theory. The definition of the analogs of these plus minus Selma groups does not involve these any analogs of these halves of rational points at finite level. Somehow one can do this without being explicit. So that's both the strength and the weakness of the sharp flat theory.
But sorry, if you just take that statement of Maser,
yes.
Say that that's false.
That's false, yeah.
Can you give us a sense why it's false? I don't think I understand.
Let's see. Sure. Okay, so actually, you asked the question at the right time, I think. So let me just go on with my talk for 20 seconds, as I ignore you for 20 seconds, and then I'll answer your question. So M and K is the intersection of the preimage of this local condition. But now, when P is supersingular, so when P divides AP, then if you look at the if you look at this tower, if you look at the norms, what happens is that the image of these points, when you go one level lower, gets essentially multiplied by by a root of the characteristic polynomial that's involved, the x squared minus apx plus p, which in the supersingular case is a number with positive p-adic valuation. So in other words, it gets smaller and smaller. So if you take the limit to infinity, you lose all this information about the local points, and that's why the control theorem is false. Or more poetically, if you think of the control theorem as like some kind of frying pan, and then you have some pasta in there, and there's Maser at the top with a spoon, and he's controlling the pasta from the top. But in the supersingular case, somehow the spoon becomes too thin, so you cannot control this. In the ordinary case, the length of the spoon stays the same, but in the supersingular case, the length of the spoon becomes thinner and thinner and thinner, so it breaks.
That's what the referee's going to complain about?
I'm sorry? that is not. We didn't. This is like. I only do this verbally. I will not write anything like this. Anyway, so where were we? The strategy is to look at this. So step one of the strategy is control wherever you can. Maybe control whatever you can. So you have M and K, which is uncontrollable. But there's another Selma group, the fine Selma group. Which is not supposed to know the local points, but only 0. If you look at the dual of the Selma group, then if you follow the definitions through, you see that this becomes a quotient of that one. And we can analyze this quotient. So for the dual of the fine Selma group, control theorem holds. And to continue the answer to Akshay's question, so it holds precisely because there's no local points to mess things up. So the spoon does not become thinner. It was already length 0 from the beginning, kind of. since the control theorem holds the if you use similar arguments, the ZP rank is big O of P to the n. Great, so we've controlled one quotient, but this still doesn't give us the theorem, right? So what we really need to do is you want to control the kernel. So I want to show the rank of this guy is big O of P to the n. So how do we do this? Let's see. Okay, 7 minutes. Let's see how much I can say in 7 minutes. So one crucial ingredient for analyzing this is a theorem of Krokó and Monsky. They call it a lemma, but I think it should be upgraded to a theorem. From 1983. Which states that if you have a finitely generated ZPXY module script y, the ZP rank of the co-invariance of y by the Galois group of k infinity over kn is equal to the sum of the isotypical components of y, where the isotypical components are with respect to characters of this Galois group. E theta. So in view of this theorem applied to y equal to yn, so
Is there a rank on the right?
oh, that's correct. Yes.
Is that the right Galois group, or is it kn?
K infinity over kn.
What do you mean by summing over characters
You look at all. Yeah, kn over k, sorry.
Sorry, I don't understand data of rank.
Yes, it's the other way.
And what is yn?
Yn is the kernel here. Oh wait, sorry. Man, okay, it's fine. It's fine. Sorry. Yeah, this happens if you look at the board from here, and you also have a view. All right. Any other questions? Okay. So we.
So I don't know your theorem. Your standard theorems were already strange. Started with the module, then talk about what you identified as ZP
Yes.
XY as a Galois.
Yes, exactly. Yeah, I still do. So ZPXY is still the Galois group. Is secret to ZP double adjoint gal k infinity over k. So in this case, it's enough because of this theorem. It's enough to as a consequence of this theorem, to know the growth in the ZP ranks between yn and yn minus 1, it's enough to know the ZP ranks of the isotypical components with respect to the new characters. Now, this guy, yn, is a quotient of a somewhat larger object, which I will not define. So let me just say un is a purely locally defined object. And the idea is that the ZP rank of E theta un is proportional to p to the n minus p to the n minus 1, 0. So this time 0, 1, or 2. And the hope is that it is small in many cases. In fact, it's greater than 0 if and only if the determinant of a certain 2 by 2 matrix vanishes. The stars in here are analogs of localization. So you have 4 analogs of localizations. They depend on n. So the basic idea, the harder the proof is written on the board. So the rank is bigger than 0 if and only if this determinant is equal to 0. And the idea is that this thing, the determinant being equal to 0, happens rarely. Let's say c times. And once you phrase things in this way, some explicit computations with p-adic valuations allows you to prove that this this rarely is really rare. So C is bounded by a number independent of n. So if you sum everything up, then from this you get that. In the worst case scenario, your rank grows by 2 times p to the n minus p to the n minus 1. So it's 2 times p to the n times the number of times this determinant is equal to 0. And you said that this was C, and C is independent of n. So at the end, you get the rank is less than or equal to 2 times p to the n times C.